Every second, trillions of invisible particles pass straight through your body. They don't slow down, they don't stop. They go right through the Earth like it isn't there. And for decades, scientists have believed one of those particles was carrying a secret that could explain 85% of everything in the universe. They poured billions into machines cold enough to freeze sound, fired particles at each other for 10 straight years, and waited. Then came the answer. Nothing. The ghost particle doesn't exist. Or does it? If you enjoy the ride, subscribe. We begin. Picture the universe as a massive machine. Gears turning inside gears, forces pulling and pushing, particles flying in every direction at impossible speeds. For most of human history, we had no idea how any of it worked. Then, over about 100 years, a group of scientists cracked the code. They wrote it all down in something called the Standard Model of Particle Physics. And for a while, it looked like we had figured out everything. The Standard Model is the most tested, most proven scientific theory ever written. It describes the tiny building blocks that make up all matter and the forces that move them around. Atoms are built from smaller pieces called protons and neutrons. Those are built from even smaller pieces called quarks. Electrons orbit around the center and holding it all together. 3 invisible forces do the heavy lifting: the electromagnetic force, the strong nuclear force. Each of those forces has its own carrier particle, a tiny messenger that shoots between other particles and delivers the push or pull. Light itself is just a stream of these messenger particles, called photons, carrying the electromagnetic force across space. Scientists tested this model over and over. Every single time, it held up. They predicted the existence of particles before anyone had ever seen them, and then built machines powerful enough to prove those predictions right. In 2012, a team at a giant underground accelerator in Switzerland flipped on the most powerful particle smasher ever built and found the last predicted piece of the puzzle: the Higgs boson, the particle that gives other particles their mass. The room erupted. Grown scientists cried. It felt like the final chapter of a very long book. But the celebration was short-lived. The Standard Model, for all its brilliance, has cracks. Big ones that have been there since the beginning and refuse to close. The model says nothing about gravity, the force that holds you to the ground, that keeps the moon circling Earth, that shapes the path of every planet in the solar system, has no place in the model's equations. Gravity is simply missing. Scientists know it exists, they can measure its effects perfectly, but the model cannot explain what actually carries it at the particle level. There is a second crack, even harder to look at. 85% of all the mass in the universe is missing. Galaxies are spinning faster at their edges than they should be. Light bends around empty patches of space where nothing visible exists. Something enormous is out there, something that has gravity and mass, but produces zero light. Scientists call it dark matter. The Standard Model has no particle for it. And then there is a third crack. When the universe was born, matter and antimatter should have been created in equal amounts. They should have destroyed each other completely, leaving nothing behind. Instead, a tiny imbalance survived. That imbalance became every star, every planet, every atom in your body. The model cannot explain why that imbalance existed. 3 enormous holes, 3 mysteries that the greatest scientific framework ever built, simply cannot answer. So physicists did what scientists always do. They looked deeper. They proposed new particles, hidden ones that the model missed, particles that could plug all 3 holes at once. And the hunt began. What they found along the way will change how you see the universe forever. Hold your hand up for 1 second. In that single second, about 100 trillion neutrinos passed straight through it. They came from the sun. They traveled 93 million miles through space. They hit the Earth and kept going, straight through the rock and iron and magma in the planet's core, and out the other side, without touching a single atom. Your hand was in the way for a fraction of a heartbeat and they never noticed. That is what a neutrino is, the most common particle in the universe that almost nothing can stop. Neutrinos are produced everywhere. The sun makes them by the trillions every second as it burns through hydrogen. Supernovas release more neutrinos in a few seconds than our sun will produce in its entire lifetime. Nuclear reactors on Earth create them constantly. Even the natural radioactive decay happening inside rocks beneath your feet generates a slow, steady stream. The universe is absolutely soaked in them. And yet, for a particle so common, they are nearly impossible to catch. The reason is that neutrinos barely interact with anything. Most particles in nature feel at least one of the forces the Standard Model describes. Electrons feel the electromagnetic force. Quarks feel the strong nuclear force. But neutrinos only feel the weak nuclear force, which is incredibly short range, and gravity, which at the particle level is so faint it is almost meaningless. So neutrinos just pass through normal matter like it is not there. To a neutrino, a block of lead 1 light-year thick, that is about 6 trillion miles of solid metal, would only stop about half of them. That sounds like a superpower, and in a way, it is, but it also makes them maddening to study. To actually catch a neutrino, scientists build enormous detectors, usually filled with ultra-pure water or liquid metal, and they bury them deep underground. The rock above shields the detector from other particles like cosmic rays, so that when something does interact inside, there is a real chance it was a neutrino. Even then, in a tank holding thousands of tons of material, only a handful of neutrinos will actually interact on any given day. The rest pour through like the detector is made of air. Here is what makes them stranger still. Neutrinos have 3 different types, called flavors. Scientists call them the electron neutrino, the muon neutrino, and the tau neutrino. And as a neutrino travels through space, it switches between these 3 flavors on its own. A neutrino that leaves the sun as an electron neutrino might arrive at Earth as a muon neutrino. This shape-shifting is called neutrino oscillation, and discovering it in the late 1990s won a Nobel Prize. It also revealed something shocking. For a particle to oscillate between types, it has to have mass, even a tiny one. The Standard Model originally predicted neutrinos were completely massless. The discovery of oscillation proved the model wrong on one of its own particles. The rulebook had a typo. That one typo sent a wave through the physics community. If neutrinos had mass and could change flavor, maybe there were more flavors nobody had found yet. Maybe there was a 4th type lurking just outside what the detectors could see. A ghost hiding behind the ghost. And that idea, small at first, would eventually consume a decade of science, billions of dollars, and one of the most ambitious experiments ever built. In 1995, a team of physicists working in the desert outside Los Alamos, New Mexico, fired up a detector called the Liquid Scintillator Neutrino Detector. They were not trying to make history. They were running what seemed like a straightforward experiment. Fire a beam of muon neutrinos at a tank of mineral oil and count how many electron neutrinos appeared on the other side. Neutrinos oscillate, so some should show up as a different flavor after traveling a short distance. The math was clear. The results were not. Too many electron neutrinos appeared. Way too many. The number was so far above what the math predicted that the team ran the analysis again and again. They checked every piece of equipment. They looked for errors in their calculations. They spent months going over every step of the process. The excess was still there, stubborn and unexplained. The 3 known neutrino flavors, the electron, muon, and tau types, could not account for what the detector was seeing. If the math of oscillation was right, the only way to get that many extra electron neutrinos was if the muon neutrinos were first oscillating into a hidden 4th type, then oscillating again into electron neutrinos. A 2-step transformation through an invisible middle state. That hidden middle state got a name, The sterile part was deliberate. Where regular neutrinos at least feel the weak nuclear force, this fourth type was theorized to feel absolutely nothing. No electromagnetic force, no strong force, no weak force. The only thing it could interact with was gravity, a particle so detached from the rest of matter that it would pass through everything in the universe without leaving a single mark, even more invisible than the neutrinos already known. The Los Alamos result caused a stir. Other experiments looked for the same signal. Some found hints that lined up. Others came up empty. For years, the evidence sat in an uncomfortable middle ground, too strong to ignore, too weak to confirm. Physicists argued at conferences. Papers flew back and forth. The sterile neutrino became one of the most debated ideas in modern science. Then something happened that pushed the debate into high gear. In 2011, scientists re-examined data from nuclear reactors and noticed a similar pattern. Reactors produce enormous quantities of electron antineutrinos, the antimatter twins of regular neutrinos. When researchers updated their calculations using newer, more accurate models of how reactors work, they found that the detectors had been measuring fewer neutrinos than the new math said should be there. About 3% fewer, consistently, across multiple reactor experiments worldwide. The gap was small, but persistent. This became known as the reactor antineutrino anomaly. Physicists proposed that the missing 3% was vanishing into sterile neutrinos during travel, oscillating away into a flavor the detectors could not see. Two separate experiments, one using a particle accelerator, one using nuclear reactors, both pointing in the same direction. The sterile neutrino started to feel less like a rumor and more like something real. But there was a problem nobody wanted to say out loud. The detector at Los Alamos had known flaws. The reactor models used in 2011 were later found to have their own errors. The anomalies were real, but their cause was still an open question. Were the numbers pointing at a new particle, or at mistakes in the measurements? One experiment was going to answer that question once and for all, and it was going to take a decade to get there. To understand why the sterile neutrino became such a big deal, you have to understand what it was supposed to solve. Physics had three open wounds. Dark matter, the source of 85% of all mass in the universe, was completely unidentified. The standard model's description of neutrino masses was incomplete. And the reason the universe has any matter at all, instead of pure emptiness after matter and antimatter cancelled each other out, was still a mystery. Three separate problems, each one enormous on its own. The sterile neutrino, if it existed, could potentially stitch all three together. Start with neutrino mass. The standard model can be extended using a mathematical trick called the seesaw mechanism. The idea is elegant. For every normal light neutrino we detect, there exists a paired particle at the other end of a mathematical lever. Push one side down, the other goes up. The normal neutrino is feather-light. Its sterile partner would be enormously massive, perhaps millions or billions of times heavier than any particle we have ever detected. The math balances perfectly, but it requires the heavy partner to actually exist. Now fold in dark matter, a sterile neutrino massive enough, somewhere in the range of thousands of electron volts to a few kilo-electron volts in mass, would behave almost exactly like dark matter is expected to behave. It would feel no forces except gravity. It would clump around galaxies due to its mass, creating the invisible scaffolding that keeps galaxies from flying apart. It would produce no light. It would be undetectable by any conventional means. On paper, it fit perfectly. And on the matter-antimatter imbalance, heavy sterile neutrinos decaying in the early universe could have produced slightly more matter than antimatter through a process called leptogenesis, a tiny tilt in the scale, just enough to leave behind the universe we live in. One particle, three solutions. For physicists, that kind of elegant answer is almost irresistible. But elegant answers have a bad history in physics. Nature does not care about elegance. The sterile neutrino also had a practical appeal. It could, in theory, be light enough to produce in laboratory experiments. Unlike some theoretical particles that would require energies we could never reach, certain versions of the sterile neutrino might show up as a small but measurable distortion in existing neutrino beams. Scientists just needed a sensitive enough detector and enough data. The catch was its defining feature. It interacts with nothing directly. Every method of detection in physics relies on a particle leaving some kind of trace. Photons hit sensors. Electrons ionize material. Quarks spray into secondary particles when they collide. Detection means interaction. But the sterile neutrino, by definition, interacts with nothing you can measure. You cannot catch it directly. You can only look for the hole it leaves behind, a deficit in the particles that should be there, or an excess of something that appeared after passing through the hidden fourth flavor. You are hunting a shadow, a shape defined entirely by what is missing around it. That is what made the anomalies from the 1990s so compelling. Something was creating gaps and excesses that the three known neutrino types could not explain. The shape of the shadow was exactly the right size for a sterile neutrino. Whether the shadow had a body behind it, that was still the question. And the answer was being built underground in Illinois. About 30 miles west of Chicago, buried in a complex of underground tunnels and experimental halls, sits one of the most powerful particle accelerator facilities on Earth. Fermilab has been smashing particles since 1967. It discovered the bottom quark, the top quark, and the tau neutrino. If you want to hunt the rarest and most elusive particles in existence, this is the address. In 2015, a new experiment came online there. It was called the Micro-Booney detector, and its job was simple in description, brutal in execution. Find the sterile neutrino or prove it does not exist. The detector itself looked nothing like the sleek machines you might picture from science fiction. From the outside, it was a large silver cylinder, about 12 meters long, roughly the length of a city transit bus. Inside was something unusual: 85 tons of liquid argon. Argon is a gas at room temperature, a completely invisible element that makes up about 1% of the air you breathe. To turn it into liquid, you chill it to nearly 300 degrees below 0 Fahrenheit. At that temperature, it becomes a crystal clear, ultra-pure liquid with a remarkable property. When a charged particle passes through it, the argon atoms release electrons which drift through the liquid and hit a series of wire sensors on the walls of the tank. Those wire signals are translated into an incredibly detailed three-dimensional image of whatever just happened inside. Think of it like a giant, super-cold lava lamp, where every bubble is a charged particle and you can photograph every single movement in 3 dimensions. The Micro-Booney detector was deliberately placed along 2 simultaneous neutrino beams. The first beam came from Fermilab's accelerator, directly. The second came from a different direction, providing a cross-check. The idea was to look for the exact signal the Los Alamos experiment had seen in the 1990s, too many electron neutrinos appearing where only muon neutrinos should be. That excess would be the fingerprint of sterile neutrino oscillation. To make the detection meaningful, the team needed enormous statistics. 1 or 2 events meant nothing. Background noise, cosmic rays sneaking in from above, and random particle interactions inside the argon could all mimic a real neutrino signal. The only way to know the difference was to collect so much data that the signal would stand out like a lighthouse in a fog bank. So they ran and ran. Year after year, billions of protons accelerated and smashed to generate the neutrino beams. The detector recorded every flicker of charge in the liquid argon. Physicists developed increasingly sophisticated software to sort genuine electron-neutrino events from the background clutter. The analysis alone required hundreds of scientists working across multiple institutions on 3 continents. The technology inside Micro-Booney was so advanced that it later influenced the design of larger detectors planned for the future. Just running it successfully was a scientific achievement, but a technological achievement was never the goal. The goal was the sterile neutrino, and after nearly a decade of patient, meticulous data collection, the results were finally ready to be read. Nobody in the building was entirely sure what the numbers would say. The Microbuoy collaboration did not announce their final result at a press conference. They published it in the journal Nature in December 2025. Hundreds of scientists had worked on the analysis. The paper listed authors from universities and labs across the United States, Europe, and Asia. It was the product of a decade of effort, and the physics community had been waiting for it, with the kind of tension that builds before a verdict is read in a courtroom. The result was clean. After 10 years of operation, after analyzing billions of neutrino collisions, after developing some of the most advanced particle identification software ever written, Microbuoy found no evidence for the sterile neutrino. The excess of electron neutrinos that the Los Alamos experiment had recorded in the 1990s was gone. The data from Microbuoy matched the standard model predictions for 3 neutrino flavors, with no fourth ghost hiding anywhere in the signal. The earlier anomaly had been a measurement problem. Background noise from photons, mimicking electron neutrino events, had fooled the older detector. Microbuoy's liquid argon technology could tell the difference between a photon and an electron with far greater precision. When the two were properly separated, the excess vanished. The sterile neutrino, as described by those old anomalies, ruled out at 95% confidence. In physics, that is not a close call, that is a verdict, but the silence in the data was louder than just the death of one particle. Think about what 10 years of silence actually means. Scientists fired more particles at that detector than you can meaningfully picture. The total number of proton collisions used to generate the neutrino beams ran into the hundreds of billions. Each collision sent neutrinos streaming toward the argon tank at nearly the speed of light. Each detected interaction was catalogued, reconstructed, and checked. The detector captured neutrino events with a level of detail that previous generations of physicists would have called impossible. And across all of that data, across all that time, the sterile neutrino left no mark. Physics often celebrates discovery. Scientists get excited about finding things, but ruling something out with this level of precision is its own kind of scientific achievement. It clears the field. It tells future experiments where to stop looking. It forces the field to confront what comes next. What comes next, in this case, is uncomfortable. The sterile neutrino was supposed to explain the reactor anomaly, the Los Alamos anomaly, and potentially plug into dark matter and the neutrino mass problem. At the same time, with it gone, those explanations go with it. The reactor anomaly now appears to come from incomplete models of how reactor fuel behaves, errors in the nuclear physics calculations rather than a hidden particle. That explanation is now being verified separately. Dark matter still has no confirmed particle. Neutrino masses still lack a complete theoretical explanation. The seesaw mechanism might still work with a heavier version of the sterile neutrino far beyond current detector range, but that is a different hypothesis entirely, and a hypothesis with no experimental path to confirm it is not much better than a guess. The field picked itself up, dusted off, and looked at what was still standing. 2 other missing particles remained, and they were far stranger. December 2025 did not feel like a dramatic month for most people, but inside the particle physics community, it was a turning point. The Microbuoy paper landed in Nature and immediately rippled outward. Science journalists covered it. Physicists posted reactions. The summary was simple. A particle that hundreds of researchers had spent years chasing had been ruled out with the highest level of experimental certainty the field had ever applied to that particular question. The single sterile neutrino model, the lightweight version predicted by the 1990s anomalies, was finished. What broke alongside it was a certain kind of optimism. For about 30 years, the The sterile neutrino had served as a comfortable placeholder. When the Standard Model failed to explain something, it sat in the gap like a spare key you keep because you think it might open something someday. Dark matter gap, sterile neutrino. Neutrino mass gap, sterile neutrino. Reactor anomaly, sterile neutrino. It was a particle that promised to fix problems without being specific enough about how that anyone could prove it wrong quickly. Microburnie proved it wrong quickly. 10 years is quick in physics. The immediate impact hit several ongoing research programs. Teams that had been designing follow-up experiments to study sterile neutrino properties had to pivot. Funding proposals built around the assumption that Microburnie would confirm the anomaly had to be rewritten. Theoretical models that required the lightweight sterile neutrino to make their numbers work had to be retooled or abandoned. The broader impact was harder to measure, but more important. When a particle physicists expected to find does not appear, the field is forced to ask whether it was looking in the right way, using the right ideas. The Standard Model was already known to be incomplete, but every failed search for something beyond it raises the possibility that the extensions physicists have been proposing are also wrong. The sterile neutrino was not just one particle. It represented an entire family of theoretical approaches based on adding new neutrino types to the model. With the lightweight version ruled out, heavier versions remain on the table, but they require completely different detection strategies and energy scales. The elegant triple solution that one particle would explain dark matter, fix neutrino masses, and explain the matter-antimatter imbalance, that specific version of the story is over. The universe did not cooperate with the clean answer. There is a second particle that physicists have been hunting even longer and failing even more completely. It does not interact weakly or strongly or electromagnetically. It interacts through gravity alone, and detecting it would require a machine so impossibly large that building one borders on absurd. The graviton, the particle that carries the force keeping your feet on the ground. It has never been seen, and the reason why reveals something deeply strange about the universe's most familiar force. Stand outside on a clear night and look up. Everything you see, every star, every smear of the Milky Way, every pinprick of light, all of it is made of the same basic ingredients. Quarks bundled into protons and neutrons, electrons circling around them, photons flying between atoms and carrying energy from one place to another. The Standard Model describes all of that with breathtaking precision. Now imagine the model is a map of a city. It shows you every building, every road, every address. You can navigate every block. But on the map, 3 entire neighborhoods are just blank white space. No roads, no buildings, just nothing. And those 3 blank neighborhoods together are bigger than everything the map does show. That is the Standard Model's situation. The first blank neighborhood is gravity. The Standard Model describes forces using carrier particles. The electromagnetic force uses photons. The strong nuclear force uses particles called gluons that hold quarks together inside protons. The weak nuclear force uses particles called W and Z bosons that control radioactive decay. Every one of these forces has a particle messenger. But gravity, the force that pulls masses together, has no such particle in the model. Scientists believe one must exist, and they have named it the graviton. But the model cannot describe it, and no experiment has ever detected one. The gap here is enormous. Gravity governs the motion of planets, stars, galaxies, and the large-scale structure of the universe. General relativity, Albert Einstein's theory of gravity, describes it as a smooth curve in the fabric of space and time. Quantum mechanics, the theory that the Standard Model is built on, describes everything in terms of discrete particles and probability. These 2 frameworks are both incredibly accurate within their own domains, but they are mathematically incompatible. When you try to combine them, the equations break down and produce nonsensical infinities. For physics to have a complete theory of everything, Gravity must be made quantum. The graviton is the particle that would do that job. The second blank neighborhood is dark matter. Astronomers have measured its effects on galaxies, on light, on the structure of the universe. They know, with no room for doubt, that something massive and invisible is out there. But after decades of searching, no experiment has identified what it is made of. The Standard Model has no particle that fits. The third blank neighborhood is the matter-antimatter imbalance. When energy creates particles, it creates equal amounts of matter and antimatter. Matter and antimatter destroy each other on contact. The Big Bang should have produced equal amounts of both, and they should have annihilated each other completely, leaving an empty universe full of pure energy. Instead, a tiny surplus of matter survived. Every atom in your body exists because of that surplus. The model predicts the imbalance should be almost zero. The universe shows it was just enough. 3 blank spaces, 3 problems that the most successful theory ever written cannot touch, and each one points toward a missing particle that should exist somewhere just outside our reach. Picture 2 kids on ice skates throwing a basketball back and forth. Every time one throws, they get pushed backward. Every time the other catches, they get pushed back too. The ball is what transfers the force between them. Neither kid reaches out and grabs the other directly. The ball does the work. That is how forces work at the particle level. 2 electrons do not directly repel each other. One electron fires a photon, a particle of light, and the other electron absorbs it. The exchange of that photon carries the electromagnetic force between them. Zoom in close enough, and every push and pull in nature works like that basketball exchange, particles throwing invisible messenger particles back and forth constantly. This is the quantum picture of forces, and it is extraordinarily well tested. The photon mediates electromagnetism, and we have built entire industries around controlling it. The gluon mediates the strong nuclear force, the one that holds quarks inside protons and neutrons. And our understanding of it explains why atomic nuclei hold together. The W and Z bosons mediate the weak nuclear force responsible for radioactive decay, and our knowledge of them made nuclear medicine possible. 3 forces, 3 sets of carrier particles, all confirmed in experiments, all mathematically consistent with each other in a framework called quantum field theory. Gravity stands alone. Einstein described gravity as geometry. Mass bends space and time, and other objects follow those curves. An apple falls because Earth curves the space around it, and the apple follows that curve the same way a marble rolls toward the center of a bent rubber sheet. This picture is extraordinarily accurate. Scientists use it to navigate spacecraft across the solar system, with precision measured in miles over journeys of hundreds of millions of miles. But Einstein's gravity is smooth. It is continuous. It does not come in packets. Quantum mechanics, on the other hand, says everything comes in discrete packets. Energy, charge, spin, all of it is quantized. The 2 descriptions work beautifully in their own domains, but fall apart when you try to use them together. For an electron near a black hole, you would need both theories at once. Einstein's gravity for the curvature of space, quantum mechanics for the behavior of the electron. But when physicists try to write a single set of equations covering both, the math produces answers like infinite energy and infinite probability, which is physics language for something has gone very wrong. In theory, is to quantize gravity, to say that gravity is also carried by a particle, a messenger that travels between masses, the same way photons travel between charges. That particle is the graviton. If the graviton exists, it would travel at the speed of light, have no mass, and carry spin 2, twice the spin of a photon. All of that can be derived from the math without ever detecting one. The predictions are precise. The particle is logically required. The problem is catching it. Gravity is roughly 1 million billion times weaker than electromagnetism. Even with a perfectly designed detector The chance of a graviton interacting with it in any measurable way is nearly impossible to calculate without arriving at a number that looks like a joke. What that number looks like in practice is exactly where things start to feel surreal. Every great unification in the history of physics started with a question nobody thought was answerable. James Clerk Maxwell asked whether electricity and magnetism were the same thing, and produced equations that unified them completely. Einstein asked whether gravity and acceleration were the same thing, and produced general relativity. In the 1960s and 1970s, physicists unified electromagnetism and the weak nuclear force into a single framework, then pulled the strong force into the same picture. Each unification produced new predictions, new particles, new technology. Every time the universe turned out to be more elegant and more unified than it looked before. Gravity is the holdout, the last force that refuses to join the group. The graviton is the particle that would bring it in. Here is what the graviton is supposed to do. Two masses, a planet and a moon, attract each other. In the quantum picture, that attraction happens because they are constantly exchanging gravitons. The graviton carries the gravitational force across space, the same way the photon carries the electromagnetic force. The planet emits a continuous stream of gravitons in every direction. Some of them reach the moon absorbs them, feels a push toward the planet, and stays in orbit. The moon sends gravitons back. The dance continues. If this picture is right, then gravity is just another force, just another set of particles, just another chapter in the quantum mechanics playbook. Everything clicks into place. General relativity becomes a smooth approximation of a deeper quantum reality, accurate at large scales the same way a smooth glass of water is an accurate description of what is really trillions of individual water molecules. A working theory of quantum gravity would be the most powerful scientific framework ever written. It would apply everywhere, from inside black holes to the first instant after the Big Bang. It would describe the smallest possible scales of space and time, distances so tiny they make an atom look like a galaxy. It would complete the map that the Standard Model started. Every major unsolved problem in theoretical physics connects to quantum gravity. The information paradox of black holes, the nature of the Big Bang singularity, the structure of space and time at the smallest scales, all of them bottleneck at the same missing ingredient, and the graviton is that ingredient. Theoretical physicists have derived a remarkable amount about the graviton without ever seeing one. Its spin, 2 compared to 1 for photons, comes directly from the mathematics of how a spin 2 particle would behave when exchanged between masses. It must be massless because gravity acts over infinite distances. It must travel at exactly the speed of light because gravitational waves, which have been directly detected by experiment, travel at exactly that speed. When two black holes merged over 1 billion light-years away and sent ripples through space-time in 2015, those ripples arrived at Earth at the speed of light. If gravitons are the quantum carriers of those ripples, they move at the same speed. So the particle is defined. Its properties are calculated. Its role is clear. The math demands it. The problem is the math also tells us something disturbing about our ability to find it, because what the math reveals about detection makes the sterile neutrino hunt look simple by comparison. In 2003, a physicist named Freeman Dyson published a short paper that asked a deceptively simple question. Is it possible, even in principle, to detect a single graviton? Dyson's argument started with gravity's weakness. Compared to electromagnetism, gravity is so faint that the ratio between the two forces is roughly 1 followed by 36 zeros. A child's magnet can pick up a paperclip against the gravitational pull of the entire Earth. That is how enormous the gap is. To detect a single photon, you need a sensor roughly the size of a fingernail. To detect a single graviton with the same probability of interaction, you would need a detector with a mass roughly equal to that of Jupiter, the largest planet in our solar system. Jupiter's mass is about 300 times Earth's mass. Its diameter is 11 times Earth's diameter. A detector built at that scale would collapse under its own gravity and form a black hole before detecting anything. The device would destroy itself in the act of being created. Dyson's conclusion was precise. Any detector sensitive enough to detect a single graviton would, by the laws of physics, be crushed into a black hole by its own weight before a single graviton arrived. The detection problem is not a question of technology, it is a question of physical law. That is an extraordinary statement. Physics is full of things that are hard. Splitting the atom was hard, but those are engineering challenges. You build something bigger, more sensitive, more precise, and eventually you get there. The graviton problem is different. Dyson argued that the obstacle is fundamental, built into the fabric of the universe itself. There is a slight escape hatch. If a graviton detector were placed in orbit around an extremely dense object, like a neutron star, the density of gravitons near that object would be far higher than in open space. Neutron stars are the collapsed cores of dead stars, so dense that a teaspoon of their material would weigh about 10 million tons. Their gravitational fields are powerful enough to crush protons. A perfect detector near a neutron star, still requiring Jupiter's worth of mass, would theoretically detect one graviton every 10 years. One signal per decade, from a machine the size of a planet, hovering near one of the most violent objects in the universe. The practical reality is that no such detector will ever be built. The engineering barriers alone, independent of the physics barriers, are beyond any civilization that exists today or is likely to exist in any foreseeable future. What this means for physics is profound. If the graviton cannot be detected, then the quantum theory of gravity cannot be tested in the most direct way available. Science depends on experiments. A theory that cannot be tested by any conceivable experiment exists in a strange zone between physics and philosophy. Some researchers argue that the graviton might reveal itself indirectly through the behavior of other particles at extremely high energies. At the energies present just after the Big Bang, gravity would have been as strong as the other forces. The effects might show up in future collider experiments or in the patterns of ancient light left over from the universe's first moments. But for now, the graviton remains perfectly described and completely invisible, and the question of whether it exists at all is about to get far more complicated. For most of the 20th century, finding the graviton felt like an inevitability, just a matter of time, of better detectors, of more powerful colliders. The same confidence that once existed around the Higgs boson, around the W and Z bosons, around the top quark. Those particles were predicted before they were found. Eventually, the technology caught up, and there they were. But the graviton problem, as Dyson described it, is different in kind, and a growing number of physicists have started to sit with an uncomfortable possibility. Maybe gravity does not have a particle. The argument runs like this. Every other force that has a quantum description also has a force-carrying particle. But what if gravity is the exception? What if gravity is not a quantum force at all, but a purely classical effect, a smooth geometric property of space-time that emerges from quantum behavior at scales we cannot yet probe? This idea has a name: semi-classical gravity. In this picture, space-time behaves smoothly and continuously at all scales, and quantum mechanics governs the particles moving through it, but the stage itself, the geometry of space and time, stays classical. No graviton required. The two theories, quantum mechanics and general relativity, coexist without ever truly merging. The appeal of this idea is that it sidesteps the mathematical catastrophes that arise when you try to combine them. The infinities that appear in quantum gravity calculations simply go away if gravity is not quantum in the first place. The problem is that this idea conflicts with something physicists hold almost sacred, the principle of universality. Every other known interaction between particles is governed by quantum mechanics. If electrons and quarks and photons all obey the quantum rules, It seems deeply strange that the force connecting them through gravity would play by entirely different laws. The universe would be operating on two incompatible rulebooks simultaneously, one quantum, one classical, with no bridge between them. Some physicists find that acceptable, others find it catastrophic. Roger Penrose, one of the most respected mathematical physicists alive, has long argued that gravity's relationship to quantum mechanics is the key to understanding consciousness, time, and the arrow of entropy. In his view, gravity actively resists being quantized because it plays a fundamentally different role in the structure of reality. He believes the resolution will require a completely new framework, neither quantum mechanics nor general relativity, but something no one has written yet. String theory attempted to solve the problem by proposing that all particles, including the graviton, are actually tiny vibrating strings of energy. In string theory, a graviton is a specific vibrational mode of these strings. The math works out beautifully, producing a graviton with exactly the right properties. String theory also requires extra dimensions of space beyond the three we experience. If those dimensions exist, gravitons could leak into them, which would explain why gravity is so much weaker than the other forces. The graviton is not weak, it is just spreading into dimensions we cannot see. No evidence for extra dimensions has appeared. Whether or not the graviton exists, something must fill the gap it was supposed to occupy. And while theoretical physicists argue about geometry and strings and extra dimensions, experimental physicists have been chasing a completely different missing particle. One that might fill the dark matter gap, one with a name borrowed from a soap bottle. Sometime in the 1970s, an astronomer named Vera Rubin sat down with data from dozens of spiral galaxies and noticed something wrong. Galaxies spin, the Milky Way rotates, our solar system traveling around the galaxy's center at about 500,000 miles per hour. In a spinning system held together by gravity, there is a rule. The farther out you go from the center, the slower things should move. Planets in our solar system follow this rule perfectly. Mercury zips around the Sun at over 100,000 miles per hour. Neptune, at the outer edge, crawls along at about 12,000 miles per hour. The math of gravity predicts this precisely. Rubin expected to see galaxies behave the same way. Stars near the center fast, stars near the edge slow. Standard physics, clean and predictable. Stars at the outer edges of spiral galaxies were moving just as fast as stars near the center, in some cases even faster. If nothing invisible was holding them, those outer stars should have been flung off into deep space long ago. The galaxy should have torn itself apart. Instead, it stayed together, spinning uniformly, as if some enormous invisible mass extended far beyond the visible disk of stars, providing extra gravitational grip to keep everything in orbit. Rubin spent years measuring galaxy after galaxy. The pattern held everywhere she looked. Every spiral galaxy she examined showed the same impossible rotation curve. The data was iron solid. Something was there, something massive, something that produced gravity but emitted zero light. The scientific community resisted at first. Invisible mass sounded too convenient, too much like inventing a mystery to solve a mystery. But the evidence kept building from independent directions. X-ray telescopes showed hot gas clouds around galaxy clusters behaving as if they were trapped by far more gravity than the visible matter could provide. Studies of how galaxies collide showed the visible matter slowing down while an invisible component passed straight through, responding only to gravity. Dark matter, the name given to this invisible mass, now accounts for about 85% of all matter in the universe. Ordinary matter, every atom, every star, every planet, every galaxy, makes up only 15% of what gravity says should be there. The universe is dominated by something we have never touched, never seen, never directly measured in a laboratory. The Milky Way sits inside a dark matter halo, a roughly spherical cloud of invisible mass extending hundreds of thousands of light years in every direction. Without it, the outer arms of the galaxy would spiral away into the void. The galaxy as we know it, including every star needed to eventually produce Earth and everything on it, would not exist. Something built the structure of the universe. Something provided the gravitational scaffolding that allowed galaxies to form in the first place, pulling gas clouds together over billions of years until stars ignited and planets formed. That something has no confirmed identity. 3 serious candidates have been proposed over the decades. 2 of them have been eliminated. The third is still standing. And it has one of the strangest origin stories in the history of physics. Einstein predicted it in 1915. Astronomers confirmed it in 1919. And since then, it has become one of the most powerful tools in all of astronomy. Gravity bends light. When light from a distant star or galaxy passes close to a massive object, the mass curves the space around it, and the light follows that curve. From Earth, the star appears in a slightly different position than it actually occupies. The massive object in between acts like a lens, bending, stretching, and sometimes splitting the image of whatever sits behind it. This effect is called gravitational lensing. For ordinary matter, visible stars and gas clouds, it was already a useful tool. Astronomers could map the massive galaxy clusters by watching how they distorted the light of more distant galaxies behind them. But then something strange turned up in the maps. When astronomers calculated how much mass would be needed to produce the lensing they observed, the numbers were far larger than the mass of all visible matter in those regions. The bending was too strong. The lens was heavier than anything that could be seen. Something completely invisible was adding its gravity to the visible matter and bending light far more than the stars and gas alone could manage. Dark matter does not emit light. It does not reflect light. It does not absorb light. To ordinary photons, it is completely transparent. But it has mass, and mass bends space, and bent space bends light. So dark matter leaves a gravitational signature in the distorted images of background galaxies, even though it cannot be photographed directly. The most dramatic evidence came from something called the Bullet Cluster. 2 galaxy clusters had collided and passed through each other. The ordinary matter, the gas and plasma, slowed down during the collision due to electromagnetic drag, piling up in the middle. But the dark matter, interacting only through gravity, passed straight through the collision like the 2 clusters were made of air. After the impact, the center was hot gas glowing in X-rays. The edges where the dark matter ended up were invisible to cameras but clearly mapped by the gravitational lensing of background galaxies. The map showed exactly what the dark matter picture predicts. 2 invisible blobs separated from the visible gas, one on each side of the collision zone, their positions revealed purely by the bent light of galaxies millions of light years behind them. This observation, replicated across other colliding clusters, rules out most alternative explanations. The dark matter and the ordinary matter behave differently in a collision. That means they are genuinely different substances. Dark matter is real. It has mass, and it does not interact with light or ordinary matter except through gravity. What it is made of is a different question entirely. For a long time, the leading candidate was a class of particles called weakly interacting massive particles. Decades of experiments searched for them and found nothing. They have been largely ruled out. The sterile neutrino was the next frontrunner. That ended in December 2025. Now the field has one major candidate left, and the story of how it was invented is as strange as the particle itself. Our galaxy is enormous. From edge to edge, the Milky Way stretches about 100,000 light-years across. 1 light-year is roughly 6 trillion miles. Try to picture that distance and the number becomes meaningless. So instead, picture this. If the entire Milky Way were shrunk down to the size of the United States, our solar system would be a single grain of sand somewhere in the middle of Kansas. Everything in that vast disk is rotating. the entire galaxy spins like a slow, enormous hurricane, making one full rotation roughly every 230 million years. Our solar system has completed that loop about 20 times since Earth formed. We are spinning right now, hurtling around the galaxy's center at around 500,000 miles per hour, and it feels like standing still. Now imagine removing dark matter. The outer stars of the Milky Way, the ones in the thin stretched arms spiraling away from the center, are already moving fast. Without an invisible mass extending far beyond the visible disk, those stars would have more than enough speed to escape the galaxy entirely. The gravitational pull of the visible stars and gas near the center would be nowhere near strong enough to hold them. One by one, the outer arms would peel off, stars would drift away into the intergalactic void. The spiral shape we know would dissolve. This is not a hypothetical concern. Astronomers have simulated it. Remove dark matter from a galaxy model and watch what happens. The disk destabilizes within a fraction of a rotation cycle. Stars scatter, the elegant spiral structure collapses. What is left is a much smaller, much denser clump of matter in the center, surrounded by a scattering of escaped stars drifting away with nowhere to go. Now scale that up. Dark matter does not just hold individual galaxies together, it built the large-scale structure of the universe. In the very early universe, ordinary matter was spread almost perfectly evenly. On its own, it would have taken a very long time to clump into the first galaxies. Dark matter clumped first, forming enormous webs of invisible scaffolding called the cosmic web. Ordinary matter fell into those webs, concentrating along the threads and at the intersections where the scaffolding was densest. That is where galaxies formed. That is where stars formed. The cosmic web of dark matter is the reason the universe looks the way it does. Vast filaments of dark matter stretching hundreds of millions of light years, with galaxy clusters at every junction. Enormous, empty voids between the filaments, a structure that looks, from above, like a massive three-dimensional spiderweb, or the neural connections inside a brain. Without dark matter, that web never forms. Galaxies take too long to clump together. Stars ignite too late, or never. The conditions for planets, for chemistry, for life, all of it comes down to whether that invisible scaffolding was there at the start. The universe you live in exists because of something you have never seen and cannot touch. Finding out what that something is made of has become one of the most urgent questions in all of science, and the best remaining candidate has a backstory nobody expected. In 1977, two physicists named Roberto Peccei and Helen Quinn were not thinking about dark matter at all. They were trying to fix a completely different problem, one buried deep in the equations of the strong nuclear force. The strong force is the one that holds quarks together inside protons and neutrons. Its mathematical description is one of the most precisely tested theories in physics. But buried inside those equations is an awkward term, a free parameter that physicists call theta. In principle, theta can take any value between 0 and 2 pi, a full circle's worth of possible numbers. Its value controls how much the strong force violates a symmetry called charge parity symmetry. Essentially the question of whether the strong force behaves differently for matter versus antimatter. Experiments show the strong force does not violate this symmetry, or if it does, the violation is so tiny it has never been detected. The value of theta, measured from experiment, is less than 1 part in 10 billion, that is, extraordinarily close to 0. The problem is, there is no reason in the standard model for theta to be that small. It could be any value. The fact that it is essentially 0 looks like a coincidence, a fine-tuned accident, and physicists deeply distrust coincidences that look like fine-tuning. When a number is suspiciously small with no explanation, it usually means something is missing from the theory. Peccei and Quinn found a mathematical fix. They proposed a new symmetry in nature that would naturally drive theta towards 0. The equations automatically stabilize at the value that matches what experiments see. The fine-tuning disappears because the symmetry does the work, but every new symmetry in physics comes with a corresponding particle. When a symmetry is broken even slightly, it produces a ripple in the quantum field associated with that symmetry, and that ripple behaves like a particle. Frank Wilczek, who later won a Nobel Prize in physics, worked out what this new particle would look like. He named it the Axion, borrowed from a brand of laundry detergent popular at the time, because the particle was cleaning up a messy problem in the equations. The Axion turned out to be extraordinarily light, billions of times lighter than a single proton, so light that you could fit an unimaginable number of them in a very small space without it adding up to much mass at all. And then someone noticed something remarkable. If axions are that light and were produced in enormous quantities right after the Big Bang, they would be everywhere. They would fill the universe like an invisible fog, too light to move fast enough to escape any gravitational well. They would clump around galaxies. They would provide gravitational mass without emitting light, without interacting electromagnetically, without registering on any conventional particle detector. They would behave exactly like dark matter, a particle invented to solve a math problem. In the strong nuclear force turned out to be the perfect description of the universe's biggest mystery. That is either a remarkable coincidence or a sign that something very real has been sitting in the equations, waiting to be recognized for nearly 50 years. The naming story is worth pausing on because it says something real about how science actually works. Frank Wilczek was a young physicist in the late 1970s when he calculated the properties of the particle that Peccei and Quine's symmetry required. He was rigorous in the mathematics. He derived the particle's mass, its coupling strength to other particles, how it would decay, how it would be produced. All of that was serious, careful science. But when it came time to name the particle, Wilczek looked at what it was doing in the equations. The Peccei-Quine symmetry was introducing a new field that swept through the quantum description of the strong force and cleaned out the problematic theta term. It was, mathematically, scrubbing away an ugly mess in the theory and leaving the equations clean. Wilczek was in a grocery store. He saw a box of Axion brand laundry detergent on the shelf. The product claimed to clean clothes. The particle cleaned equations. He wrote it down. The name stuck, and the physics community accepted it with the mild amusement that tends to greet unconventional choices. Particle naming has always had a range. Quarks got their name from a line in James Joyce's novel Finnegan's Wake. The Higgs boson is named after Peter Higgs, who did not want it named after him. The gluon is named for what it does. It glues quarks together. Charm, strange, top, bottom are quark flavor names, chosen somewhat arbitrarily. Physics has never had a strict naming committee. But the Axion's origin story carries a deeper point. Wilczek was not thinking about dark matter in 1977. No one was. Dark matter as a concept existed, but the evidence was still being gathered. The Peccei-Quine symmetry was a solution to a specific narrow problem inside the strong force. The axion was a byproduct of that solution, a necessary particle that the math demanded. 20 years later, as cosmologists mapped the structure of the universe, and astronomers like Vera Rubin continued quantifying the impossible rotation of galaxies, theorists started looking for dark matter candidates. They needed a particle that had no electric charge, did not interact with light, had some mass, was produced in the early universe in large quantities, and moved slowly enough to clump into galaxy-shaped structures. They ran through the checklist for the axion. No electric charge? Check. No interaction with light? Check. Extremely light mass produced in huge numbers after the Big Bang? Check. Slow-moving enough to clump gravitationally? Check. The match was essentially perfect. A particle designed as a mathematical cleanup tool turned out to be the ideal description for the substance making up 85% of all mass in the universe. The universe had hidden its biggest secret inside a solution to a completely unrelated problem. This kind of cross-domain surprise is actually common in physics history. The mathematics of one problem turns out to describe a completely different phenomenon. Imaginary numbers developed for algebra turn out to be essential for quantum mechanics. Equations for heat flow turn out to describe the spread of diseases. The deep structure of mathematics appears to be connected to the deep structure of reality in ways that physicists do not fully understand. The axion sits at the center of that mystery right now. The math says it should exist. The universe's missing mass says something should exist. The two descriptions match. Whether the match is real is what the next generation of experiments is about to find out. And the method scientists are using to look for something billions of times lighter than a proton is stranger than the particle itself. The axion has one known weakness. In the presence of a powerful magnetic field, an axion can convert into a photon, a particle of light. The math behind this was worked out in the 1980s, and it gave experimenters their only real handle on something otherwise completely invisible. You cannot build a trap that catches an axion directly, but if the conditions are right, the axion announces itself by briefly becoming light. The energy of the photon it produces matches the mass of the axion almost exactly, converted through Einstein's famous equation. Because axions are so light, the photons they produce fall in the microwave range, the same frequencies used by radar systems and microwave ovens. The signal would be faint, extremely faint, but faint is not the same as impossible. The device designed to catch this conversion is called a haloscope. The basic design sounds almost simple. You take a metal cylinder, cool it to temperatures colder than the void of outer space, fill it with an enormous magnetic field, and then listen for a microwave signal at the exact frequency corresponding to the axion's predicted mass. The cold temperature is essential because heat generates random microwave noise, and a warm detector would drown out the tiny axion signal completely. The whole thing has to be quieter than almost anything on Earth. The leading haloscope experiment is called the Axion Dark Matter Experiment, running at the University of Washington. Its magnetic field runs at about 8 Tesla, roughly 160,000 times stronger than Earth's own magnetic field. Even at that field strength, the expected axion signal would be so small that the experiment had to develop quantum-limited amplifiers, devices that measure electrical signals at the absolute minimum noise level allowed by the laws of physics. Any noisier, and the axion would vanish into the background. There is a catch that makes this far harder than it sounds. Physicists do not know the exact mass of the axion. The Peccei-Quinn symmetry constrains it within a range, but that range spans many orders of magnitude. A haloscope only listens at one frequency at a time. Tuning it to a different frequency means physically adjusting the cavity inside the detector. To scan through the full range of possible axion masses, you would need to scan through billions of individual frequency steps, spending enough time at each one to either detect a signal or rule it out with confidence. At current scanning speeds, covering the entire theoretically allowed range would take longer than the age of the universe. So, experimenters are working on upgrades, more powerful magnets, better quantum amplifiers, multiple cavities running simultaneously at different frequencies, new techniques using quantum squeezing, a method that exploits the uncertainty principle to reduce noise below the standard quantum limit in one measurement direction, at the cost of increased noise in another direction that does not matter for detection. The scanning rate is improving every few years. What once would have taken millions of years to cover is now projected to be achievable within decades, assuming the axion falls within the most theoretically favored mass window. That window is being narrowed from both sides by theoretical constraints and by experiment. Every frequency ruled out is a step closer to an answer, and somewhere in that range, something might be listening back. Imagine waking up to a news alert that reads, "Dark matter identified." The confirmation of the axion would be one of the most significant scientific announcements in human history. not because it would immediately change anything in daily life, but because of what it would unlock. Every piece of physics built on the assumption that dark matter exists, but is unidentified, would suddenly have a foundation. The scaffolding holding up decades of cosmological theory would be nailed down. For particle physics, the axions confirmation would rewrite the Standard Model's extensions. The Pecchier-Quinn symmetry would be confirmed as a real feature of nature. Theorists would immediately begin looking for related particles and fields predicted by that same symmetry. The family of undiscovered particles associated with this mathematical framework, called axion-like particles, would become the next generation of targets. A single detection would open an entirely new branch of experimental physics. For cosmology, it would complete the census of the universe. Right now, the breakdown of what the universe is made of has a gaping unknown at the center. Roughly 5% is ordinary matter, the atoms and molecules we interact with. About 27% is dark matter, unknown. About 68% is dark energy, even more unknown. Confirming the axion would close one of those three unknowns. The universe would, for the first time, have a known composition. For technology, the consequences are harder to predict, but historically large. Every major particle discovery eventually produced practical applications nobody anticipated at the time. The electron was discovered as a pure physics curiosity. It became the foundation of every electronic device on Earth. Quantum mechanics was developed to understand atomic behavior. It now runs every computer chip, laser, and medical scanner in existence. What axion physics would eventually produce is genuinely unknown, but the pattern of history suggests the applications would be profound and unpredictable. Now flip the scenario. If decades of increasingly sensitive haloscope searches come up empty, and if the axion's predicted mass window is fully scanned and produces no signal, the consequences for physics are harder to absorb. The Pecchier-Quinn symmetry would be dead. The strong force theta problem would return with no solution. Dark matter would have no leading candidate left. The field would be back to a blank page with no confirmed particle to point toward and no theoretical framework pointing clearly at what to try next. Some physicists already speak quietly about this possibility. A few argue that if the axion fails, the answer might not be a particle at all. Dark matter could be primordial black holes, microscopic ones formed in the early universe, so small they have never evaporated, and so numerous they account for the missing mass. That idea has its own problems, but it stays on the table. Others argue that the failure of every particle candidate would force a confrontation with modified gravity theories. The idea that dark matter is an illusion created by our incomplete understanding of how gravity behaves at galactic scales. The axion has not failed yet. The search is still young relative to the mass range remaining, but the clock on ruling things out is running, and the physics community is watching carefully. There is a version of the dark matter story where the mystery is not a missing particle at all. In 1983, a physicist named Mordechai Milgrom proposed something that the mainstream physics community mostly ignored for decades. He suggested that the strange rotation curves Vera Rubin had found in galaxies were not evidence of invisible mass. They were evidence that our equations for gravity were slightly wrong. Newton's law of gravity works perfectly everywhere it has been tested, from apples falling to spacecraft navigating the outer solar system. But all of those tests happen in environments where the gravitational acceleration is relatively strong. Milgrom noticed that the strange behavior in galaxies, the flat rotation curves that implied invisible mass, always showed up at a specific threshold. When the gravitational acceleration in a region dropped below a certain tiny value, 1/10 billionth of a meter per second squared, the normal gravitational math stopped matching observations. Above that threshold, Newton and Einstein work fine. Below it, galaxies seem to have extra gravity with no extra visible mass to explain it. Milgrom proposed that gravity itself changes behavior at very low accelerations. Below the threshold, gravity falls off more slowly with distance than the standard equations predict. Instead of weakening with the square of distance, it weakens more gently. That slower fall-off would make stars in the outer parts of galaxies orbit faster than expected, exactly what Rubin observed, without any invisible mass required. This idea is called modified Newtonian dynamics, or by its initials. It makes precise predictions about galaxy rotation curves, and for spiral galaxies, it matches observations remarkably well. Too well to be a coincidence, its supporters argue. Every galaxy it has been applied to fits the formula, with no free parameters adjusted per galaxy. You plug in the visible mass and get the rotation curve out. The mainstream physics community has resisted it for several reasons. It works for individual galaxies but struggles to explain galaxy clusters where the dark matter evidence is even stronger. It does not explain the bullet cluster where dark matter and ordinary matter physically separated during a collision. It has no satisfying theoretical foundation, no deeper reason why gravity would change behavior at that specific threshold. And it has difficulty matching the large-scale structure of the universe, the cosmic web of filaments and voids that dark matter simulations reproduce so well. But the theory has not died. Researchers have developed more sophisticated versions that address some of these problems. And every time a particle dark matter search comes up empty, modified gravity gets another look. The deeper tension here is philosophical. Physics chooses between adding invisible matter and modifying the laws of gravity. Both feel uncomfortable. Invisible matter requires a substance that has never been directly detected anywhere. Modified gravity requires the laws of physics to behave differently in low acceleration environments that we have never fully explored with precision instruments. The honest answer is that neither option is proven. The debate is real and ongoing. And sitting beneath that debate is a question about the nature of physics itself. When observations do not match predictions, do you add something to the universe or change the rules? That question has no clean answer yet. Science has a complicated relationship with anomalies. An anomaly is a result that does not fit, a measurement that comes in too high or too low, or in the wrong direction. For a working scientist, an anomaly is simultaneously exciting and terrifying. It could mean a new discovery. It could mean an error in the equipment. It could mean a flaw in the theoretical prediction you were testing. All three options look the same from the outside until you do more work. The anomaly that launched the sterile neutrino hunt looked extremely clean in 1995. The liquid scintillator neutrino detector at Los Alamos saw too many electron neutrinos appearing in a muon neutrino beam. The excess was not huge, but it was consistent across the data. The team did everything right. They checked their calibrations, reanalyzed their methods, and still found the excess. They published it carefully, with appropriate caveats. The problem was the detector's core limitation. The liquid scintillator material it used, mineral oil mixed with chemicals that glow when charged particles pass through, could not reliably tell the difference between an electron and a photon. Both produced similar light signals. Photons could mimic electron-neutrino events, and neutrino beams produce a small but predictable stream of photons as background. If those photons were slightly underestimated in the background model, they would masquerade as genuine electron-neutrino interactions. That is exactly what happened. The background photon rate had been subtly miscalculated. The mineral oil detector had no way to distinguish the two signals cleanly. The excess was real in the sense that more events were counted than the model predicted, but the events themselves were photons, not electron neutrinos. Microboni's liquid argon technology solved this problem directly. A charged particle moving through liquid argon leaves a continuous trail of ionized electrons, like a thread being pulled through the liquid. A photon does not. It travels invisibly until it suddenly converts into an electron-positron pair, leaving a distinctive forked track. The difference in track shape is unambiguous. No photon could pretend to be an electron neutrino in Microboni the way it could in the older detector. When Microbuoy applied this superior discrimination to its data, the anomaly evaporated. The excess the Los Alamos experiment had recorded matched perfectly with a slightly higher than expected photon background, not with sterile neutrino oscillation. The reactor anomaly had a parallel story. The updated nuclear reactor models used in 2011 to predict antineutrino output were themselves revised in subsequent years as physicists developed more precise descriptions of how uranium and plutonium decay inside reactor fuel rods. The new models reduced the predicted antineutrino rate, closing most of the gap that had seemed to indicate missing particles. Two anomalies, both traced to incomplete models, one in a particle detector, one in a nuclear physics calculation. This is how science actually works. Anomalies drive searches. Searches reveal limitations in measurements. Better measurements eliminate the anomalies or confirm them as something real. The sterile neutrino hunt was not a failure of science. It was science doing exactly what it should. But what it leaves behind is a field with fewer signposts and more open space. And in that open space, stranger ideas are starting to get serious attention. In a research campus in southwestern Germany, a machine the size of a house has spent years doing something almost absurdly precise. The experiment is called the Karlsruhe Tritium Neutrino Experiment. Its goal is to measure the mass of the ordinary neutrino with the highest precision ever achieved. To do that, it watches a radioactive process called tritium beta decay. Tritium is a heavy form of hydrogen. When a tritium atom decays, it fires out an electron and an electron antineutrino. The energy gets split between the two particles. If you measure the maximum energy an electron can carry, you can calculate the minimum mass the neutrino must have, because some energy always goes into making the neutrino's mass. The detection method requires extraordinary cleanliness. The tritium source must be almost perfectly pure. The spectrometer measuring the electrons must have near zero background noise. Any contamination, any stray particle hitting the detector and mimicking a real event would corrupt the measurement. The team spent years building, calibrating, and testing before taking a single data point. Over 259 days of operation, the detector collected 36 million electron events, each one carefully reconstructed, checked for quality, compared against the theoretical prediction. Out of those 36 million, the team focused on a tiny fraction, the highest energy electrons, the ones near the cutoff that carries information about the neutrino's mass. The result they published set the tightest upper limit ever placed on the neutrino's mass. The neutrino weighs less than 0.08 of an electron volt, making it at least 10 million times lighter than an electron. That number matters for the sterile neutrino story in a specific way. Some versions of the sterile neutrino model predicted it would appear as a small kink in the electron energy spectrum, a slight distortion caused by the neutrino briefly oscillating into a sterile type during decay. The Karlsruhe experiment's data was precise enough to look for that kink. It found nothing. The electron energy spectrum was smooth, exactly matching the three-flavor standard model prediction. Another door closed. The significance goes beyond the sterile neutrino specifically. Knowing the neutrino mass, with this precision, tightens constraints across a huge range of theoretical extensions to the standard model. Anything that predicts a heavy sterile neutrino appearing in beta decay at accessible energy scales gets ruled out. The parameter space for new physics narrows every time a precise measurement like this comes back clean. There is a version of scientific progress that feels triumphant, a new particle found, a theory confirmed. And there is another version, quieter but equally important, where measurements come back clean and tidy, and the universe says no to one more proposed answer. The Karlsruhe experiment ran its first phase, published its results, and has since begun a second phase with improved sensitivity. Each phase rules out more parameter space. Each null result forces theorists to be more specific about what they are predicting. The combination of Microbuoy, the Karlsruhe experiment, and the reactor anomaly updates together form a tight cage around the sterile neutrino's most accessible hiding spots. What hides deeper, at higher masses and weaker couplings, is still dark. And reaching it requires machines that do not yet exist. The graviton's detection problem is so extreme that some physicists have started asking a harder question. What if the problem is not engineering? What if gravity is simply not the kind of thing that has a particle? Every other force in the Standard Model is what physicists call a gauge force. It arises from a specific type of mathematical symmetry, and when that symmetry is slightly broken, or when you add energy to the field, particles pop out. The photon, the gluon, the W and Z bosons, all of them emerge from this same mathematical pattern. They are quantized, which means they come in discrete, indivisible packets. But gravity does not arise from the same type of symmetry. General relativity describes gravity as the curvature of spacetime itself, not as a field in the same sense as electromagnetism. The geometry of the universe responds to mass and energy, and other masses move along the paths that geometry defines. There is no obvious quantum structure hiding underneath this picture. The smooth, continuous mathematics of general relativity seems to be doing something fundamentally different from the quantum field theories describing the other forces. One of the most serious attempts to reckon with this comes from a physicist named Jonathan Oppenheim, who published a framework in 2023 proposing that space-time might be fundamentally classical, meaning non-quantum, while everything else in the universe obeys quantum mechanics. In his model, gravity and quantum mechanics are not incompatible enemies waiting to be unified. They are genuinely different categories of thing, operating by different rules, coexisting without ever needing a reconciliation. This is called a post-quantum theory of gravity. The mathematics allows for specific testable predictions. In particular, it predicts that mass measurements of any object would carry a tiny random jitter, a small unavoidable uncertainty in how strongly gravity couples to quantum systems. This jitter would be distinct from the uncertainties predicted by standard quantum mechanics and could potentially be measured with extremely sensitive experiments. The idea is controversial. Most physicists still expect gravity to be quantum in some form, because the alternative seems to require abandoning the principle that the same laws apply everywhere. If electrons obey quantum mechanics and gravity does not, then, near a black hole or at the earliest instant of the Big Bang, you would need two different rulebooks operating simultaneously with no explanation for why the universe chose to keep them separate. But the failure to find the graviton experimentally, combined with the mathematical catastrophes that arise when you try to write a standard quantum field theory of gravity, has kept these alternative ideas alive and growing. String theory, loop quantum gravity, causal dynamical triangulations, each approach takes a different angle on the same problem. None has produced a testable prediction confirmed by experiment. Each represents a serious attempt by serious physicists to find the right language for something the universe has not made easy to read. The deepest possibility is that quantum mechanics itself is incomplete, that at some scale, far below what any experiment has probed, the rules change again. If gravity is smooth all the way down, the graviton is a mirage, and the search for it ends not in failure, but in recognition that the question was wrong from the start. In the 1980s, string theory arrived with extraordinary confidence. The basic idea replaced point-like particles with tiny one-dimensional strings, loops of energy vibrating at different frequencies. Different vibrations produced different particles, the same way different vibrations on a guitar string produce different musical notes. A string vibrating in one mode was an electron. Vibrating in another mode, it was a quark. And one particular vibrational mode produced a massless spin 2 particle, the graviton. String theory did not just allow for quantum gravity, it demanded it. The graviton fell out of the math automatically. Physicists were genuinely excited. For the first time, a framework existed that could, in principle, include all particles and all forces in a single consistent set of equations. The framework required something unusual: extra dimensions. The math only stayed consistent, only avoided the catastrophic infinities that plagued earlier attempts at quantum gravity. If space-time had 10 dimensions instead of 4, we experience 3 dimensions of space and 1 of time. String theory requires 6 more dimensions of space, curled up into tiny shapes, at scales so small they are impossible to probe directly. The technical name for these shapes is Calabi-Yau manifolds, and their exact geometry determines the properties of the particles that would appear in our 4-dimensional world. One elegant consequence of extra dimensions was an explanation for gravity's weakness. The other forces live only in our 4-dimensional slice of space-time. Gravity, carried by the graviton, can leak into the extra dimensions. This leakage would dilute it, spreading the gravitational force across more dimensions and making it appear far weaker in our world than the other forces. The graviton is not intrinsically weak, it is just spreading itself thin across hidden space. If this picture were correct, the Large Hadron Collider might have produced microscopic signatures of extra dimensions. Particles disappearing into the extra dimensions would carry away energy and momentum, leaving a detectable imbalance in collision events. Small temporary black holes might form at the collider's energies if extra dimensions allowed gravity to concentrate at short distances. The Large Hadron Collider found nothing of the sort. No missing energy signatures. No micro black holes. No Kaluza-Klein particles, the specific extra-dimensional versions of standard model particles that the theory predicted would appear. Every search came back empty. String theory's defenders argue that the extra dimensions might be curled up so tightly that even the Large Hadron Collider's energies cannot probe them. The absence of a signal does not definitively rule out the theory. It constrains the parameter space. Critics respond that a theory with enough free parameters to explain any possible outcome is a theory that cannot be tested, and a theory that cannot be tested is not physics. This argument has been running for 40 years. String theory remains mathematically rich, theoretically productive, and experimentally untested. Thousands of physicists have built careers on it. Hundreds of thousands of papers explore its consequences. And it has produced real mathematics that turned out to be useful in condensed matter physics and black hole thermodynamics. But the graviton, the particle string theory was supposed to deliver, has still never been seen. The promise of unification remains where it started. On paper, physics has been chasing a single goal for over a century: one set of equations, one framework, one theory that describes every particle, every force, every interaction from the smallest possible scale to the largest structure in the universe. A theory of everything. Every major advance in physics has been a step toward that goal. Maxwell's unification of electricity and magnetism, Einstein's unification of space and time, the electroweak unification that combined electromagnetism and the weak force, the Standard Model that brought the strong force into the same language. Each step brought the dream closer. Gravity is the last step, and it is refusing to cooperate. If gravity genuinely cannot be quantized, if there is no graviton and no quantum field theory of gravity that works, then the dream of a single theory of everything may be impossible. The universe would operate on 2 genuinely separate frameworks: quantum mechanics governing the very small, general relativity governing the very large, with no bridge between them and no way to build one. For practical purposes, this might be acceptable. Engineers designing satellites use general relativity. Chemists designing molecules use quantum mechanics. Neither group needs the other's equations. The 2 theories applied in their own domains give accurate results. Most of human activity, every technology, every observation of nature, happens at scales where one or the other framework applies cleanly. The problems arise at the boundaries. Inside a black hole, quantum and gravitational effects both become important simultaneously. At the Big Bang, where all matter and energy was compressed into a space smaller than an atom, both theories are needed at once. At both boundaries, The math currently breaks down. Infinities appear. Predictions become meaningless. A universe without a theory of everything is a universe with permanent blind spots. We cannot know what happened at the first instant of the Big Bang, the moment before the universe expanded outward. We cannot know what happens to information swallowed by a black hole. We cannot know whether time had a beginning or will have an end in any meaningful sense. These are not small questions. Some physicists argue that accepting the incompleteness is itself progress. Acknowledging that the universe might be fundamentally split, that no single theory captures everything, opens up new ways of thinking about what physics is even supposed to do. Maybe the goal of a single theory of everything was always a human projection onto a universe that has no obligation to be simple. Others hold firm. The history of physics is full of apparent divisions that turned out to be artificial. Electricity and magnetism looked separate for a century before Maxwell's space and time looked separate before Einstein. The division between quantum mechanics and gravity might be the next artificial wall waiting to fall. What is certain is that the question is alive. It drives the careers of thousands of physicists right now. It shapes the design of future experiments, future colliders, future space telescopes. And the next discovery, whatever it turns out to be, will land in that open space between what we know and what we cannot yet imagine. July 4th, 2012. Geneva, Switzerland. A room packed with physicists, some of whom had been waiting for this moment their entire careers. The director of CERN stepped to the podium. The analysis from two independent detector teams at the Large Hadron Collider had been combined, checked, cross-checked, and verified. The statistical significance exceeded 5 sigma, the gold standard in particle physics, meaning the probability of the signal being random noise was less than 1 in 3 million. He announced the discovery of a new boson. The room erupted. Peter Higgs, the physicist who had theorized the particle nearly 50 years earlier, sat in the front row and quietly wiped his eyes. The Higgs boson had been predicted in 1964 as a necessary consequence of a mechanism that gives elementary particles their mass. Without it, electrons would be massless and travel at the speed of light. Atoms could not form. Chemistry would not exist. The universe would be a fog of particles flying freely through space, with no way to stick together into anything. The Higgs field, which the boson is an excitation of, permeates all of space. Particles acquire mass by interacting with this field. The stronger a particle interacts with it, the heavier the particle is. The photon does not interact with it at all, which is why light has no mass and travels at the universe's speed limit. The discovery confirmed the last unverified piece of the original standard model. Every particle the model predicted had now been found. The model was experimentally complete, and that is exactly what raised the stakes. A complete standard model, tested to extraordinary precision, that still cannot explain dark matter, gravity, or the matter-antimatter imbalance, is a model that is telling you something important. The gap between what it explains and what exists in the universe is not a technical gap. It is a conceptual gap. Something fundamental is missing. The Higgs discovery also opened a new concern. The mass of the Higgs boson, measured at roughly 125 times the mass of a proton, sits in a theoretically uncomfortable range. Standard model calculations extended to very high energies suggest this mass value should be enormously sensitive to quantum corrections from heavier particles. Without some stabilizing mechanism, the Higgs mass would be expected to run up to a value about 1,000,000 billion times larger than what was measured. That it sits at its observed value with no obvious explanation is called the hierarchy problem. The leading solution to the hierarchy problem was supersymmetry, a theoretical framework that predicted a partner particle for every standard model particle. These partners would cancel the quantum corrections and stabilize the Higgs mass naturally. The Large Hadron Collider searched for supersymmetric particles extensively. It found none. The Higgs, the one particle we did find, arrived surrounded by new mysteries. Its discovery felt like turning on the light in a room and discovering the room was much larger than expected and full of locked doors. Before 2012, there was always the possibility that the Higgs boson simply did not exist. Some theorists proposed alternatives, mechanisms that could give particles mass without a Higgs field. If one of those alternatives had turned out to be right, the Standard Model would have needed a complete rebuild from the foundations. The search for particles beyond the model would have started over from scratch. The Higgs discovery closed that escape route. The Standard Model works. Its internal structure is correct. The mechanism it describes is real. And that means the failures of the model, the 3 blank neighborhoods on the map, are not failures of an incomplete theory waiting to be replaced. They are failures of a confirmed theory that is genuinely missing something real. That distinction matters enormously. When a theory is unconfirmed and fails, you can argue about whether to trust it. When a confirmed theory fails, you have to take the failure seriously. The Standard Model has been confirmed by thousands of experiments to precision levels that would embarrass most other sciences. Every prediction it makes in its domain of applicability has been verified. So when it predicts that dark matter should not exist, meaning it has no particle for it, and dark matter demonstrably does exist, the conflict is real and deep. The Higgs discovery also provided a new tool. The Higgs boson itself is a probe of physics beyond the Standard Model. The way it decays, the rates at which it produces specific other particles, can be calculated precisely. Any deviation from those predictions would signal new physics. Experiments at the Large Hadron Collider have been measuring Higgs properties in exhaustive detail ever since, looking for the crack that points to what comes next. So far, every measurement matches the Standard Model prediction to within experimental precision. The Higgs is exactly as ordinary as it is supposed to be. That ordinariness is itself a clue. Many extensions of the Standard Model predicted that the Higgs would show deviations. Supersymmetry, extra dimensions, and composite Higgs models all made predictions about how the Higgs would behave differently from the baseline. All of those predictions have failed. The Higgs, in its exact ordinariness, is systematically eliminating the theories that were supposed to explain what comes after it. Each measurement that matches the model is a wall going up around new physics. The space where new particles can hide is shrinking. This is the uncomfortable position particle physics finds itself in after 2012. The most powerful collider ever built found the one particle it was designed to find and has found nothing else in over a decade of operation. The missing particles, the ones needed to fix the model's 3 blind spots, are either much heavier than current machines can reach, much more weakly interacting than experiments expected, or described by theories that have not yet been written. A planned upgrade of the Large Hadron Collider will push to higher energies in the coming years. A new, even larger collider has been proposed for construction in Europe over the coming decades. The energy scales that would be reached might finally be high enough to produce supersymmetric particles, or extra-dimensional signatures, or something entirely unexpected. Or they might produce nothing new at all, and the implications of that silence are something physics is beginning to seriously prepare for. Physics runs on symmetry. When a theory has a symmetry, it means the equations stay the same even after you transform something, rotate the system, mirror it. Swap a particle for its antiparticle. If the physics stays the same, the symmetry is real. And in the 20th century, physicists discovered something remarkable. Every symmetry in nature corresponds to a conserved quantity, and every conserved quantity corresponds to a symmetry. This connection, worked out mathematically by Emmy Noether in 1915, is one of the most powerful ideas in all of science. Noether's theorem says that if the laws of physics look the same no matter where you are in space, then momentum is conserved. If they look the same regardless of when you perform an experiment, then energy is conserved. Symmetry and conservation law are two descriptions of the same underlying reality. The Standard Model is built from symmetry almost entirely, the mathematical symmetry group that describes the strong force, the weak force, and electromagnetism determines which particles exist and how they interact. The particles are not added by hand, they fall out of the symmetry structure automatically. This is why theorists trust symmetry arguments when predicting new particles. If a symmetry exists in nature, it usually predicts particles, and those particles usually turn out to be real. Supersymmetry extends the standard model symmetry to include a new one, a symmetry between matter particles and force particles. For every known matter particle, supersymmetry predicts a corresponding force-like partner. For the electron, a particle called the selectron. For quarks, particles called squarks. For the Higgs, multiple partner particles. For photons, a partner called the photino. These partners would cancel the quantum corrections that make the Higgs mass unstable, solving the hierarchy problem elegantly. The symmetry argument is genuinely compelling. Symmetries that solve problems tend to be real. The electroweak symmetry was proposed to solve a consistency problem in the old theory of the weak force, and the particles it predicted, the W and Z bosons, were found exactly where the math said they would be. But the Large Hadron Collider has now searched for supersymmetric particles at energies far above what original predictions said would be needed to produce them. Nothing appeared. Theorists responded by adjusting the models, pushing the predicted masses of supersymmetric particles to higher values. New searches target those higher values. Still nothing. At some point, a theory that requires its predicted particles to be just slightly beyond every experiment's reach starts to look less like a confirmed symmetry and more like a mathematical convenience that nature has not endorsed. The axion avoids this problem. It was not invented to fix a symmetry that was demanded by aesthetics. The Peccei-Quinn symmetry was required to explain a specific, measured quantity. The smallness of theta. It made a specific prediction about what kind of particle the symmetry breaking would produce. And that prediction can be tested at energies accessible to current experiments. Symmetry as a guide to new physics is powerful, but symmetry alone, without experimental confirmation, is just a preference. The universe has demonstrated a consistent disinterest in satisfying human preferences about elegance. There is a version of the missing particle problem that physicists rarely say out loud in public, but discuss regularly in private. What if we are wrong about the equations? The standard model's extensions, supersymmetry, extra dimensions, the Peccei-Quinn symmetry, all of them start from the same assumption. The standard model is correct as far as it goes, and new physics plugs into its existing mathematical structure. The new particles obey the same basic rules. They are excitations of quantum fields. They interact through forces. They have mass and spin and charge. They are particles in the same sense that electrons and quarks are particles. But the standard model itself emerged from experiments. Physicists did not sit down and derive it from first principles. They discovered particles, measured their properties, and built a mathematical framework that fit the data. The framework happens to be based on quantum field theory, but quantum field theory was chosen because it worked, not because it is the only logically possible way to describe nature. At the scales the standard model has been tested, quantum field theory is extraordinarily accurate. The magnetic moment of the electron, a number describing how strongly electrons interact with magnetic fields, has been calculated using quantum field theory and measured by experiment to better than 1 part in a trillion. The theory and measurement agree to 12 significant figures. That is the most precise agreement between theory and experiment in the history of science. But precise agreement in one regime does not guarantee the framework applies everywhere. At energies far beyond what has been tested, at distances far smaller than any collider has probed, the framework might fail. The particles it predicts might not exist. The symmetries it assumes might not hold. Some physicists argue that the repeated failure to find particles beyond the standard model is telling us exactly this. The extensions of the model are built on the model's mathematical language, and if that language breaks down at high energies, The extensions built in that language break down with it. What replaces it is genuinely unknown. Possible frameworks include theories where space and time are not continuous, but made of discrete building blocks, or theories where particles are not fundamental but emerge from more basic geometric structures, or theories that question whether quantum mechanics applies universally at all scales. None of these alternatives has a complete working version that matches all existing data while predicting something new that could be tested. They are research programs, not theories. Work in progress. The uncomfortable position is this: physics has a spectacularly successful model with known gaps and no confirmed replacement. Every proposed replacement has failed experimentally or remains untestable. The field is in a phase where honesty requires admitting that the next big step is genuinely unclear. That is an unusual position for a science that has been so consistently successful for so long. It may also be exactly where the next breakthrough begins. The history of physics is punctuated by long stretches where nothing new appears, followed by sudden, unexpected discoveries that reframe everything. After the electron was discovered in 1897, decades passed with no new fundamental particles. Then the neutron, the positron, the muon, the pion, the kaon, all arrived in a cascade. After the Standard Model was assembled in the 1970s, particles were confirmed one by one over the following decades, culminating with the Higgs in 2012. Each confirmation took time, required new machines, demanded new techniques. The current situation is different in one specific way. Previous searches had clear theoretical targets at specific energies. Build a machine that reaches this energy, and you will find this particle. Those predictions came from well-motivated theories tested in adjacent regimes. The predictions were right. Today's missing particles, the graviton beyond reach, the axion at uncertain mass, the supersymmetric particles at perpetually adjusted energies, come with less precision. The theorists are working with less experimental guidance. The targets are real, but fuzzy. If the next generation of haloscopes for the axion covers the theoretically favored mass range with no signal, the axion is effectively ruled out at accessible scales. If the planned high-luminosity upgrade of the Large Hadron Collider finds no supersymmetric particles or extra-dimensional effects, supersymmetry at any mass scale reachable by foreseeable colliders will have been eliminated. If a proposed future collider, currently in the planning stages, finds nothing new at even higher energies, the silence will be deafening. At that point, the field faces a genuine crisis. Every leading candidate for every missing particle will have been searched for and not found. The Standard Model's 3 blank neighborhoods will remain blank. The funding pressures on experimental particle physics, already significant, will intensify. Building machines that cost tens of billions of dollars to find, nothing produces difficult conversations in government budget committees. Some researchers argue that the crisis is already here. The absence of supersymmetric particles at the Large Hadron Collider has already triggered a rethinking of the theoretical priorities that dominated the field for 30 years. The phrase nightmare scenario appeared in physics papers and conference talks after the Higgs was found with nothing else accompanying it. Others argue that the silence is simply telling experimenters to look harder at higher energies with more sensitive instruments at new observables. The universe's secrets have always required pushing to new scales. Every silence eventually ended with a signal. What gives experimentalists genuine hope is that the axion search space is finite. Unlike the graviton, the axion sits within a detectable range. Current technology is improving fast enough that the favored mass window will be fully covered within a human career's worth of research. Either the axion appears, or it does not, and the answer will be definitive. Definitive answers, even negative ones, move science forward. The next decade will close more doors than any previous decade in particle physics. What stays open after that will define the field for a generation. While theoretical debates fill conference rooms, a quieter revolution is happening in tunnels, laboratories, and refrigerated chambers around the world. The Axion search has entered an engineering phase. The physics of how to detect it is understood. The challenge is sensitivity, scanning speed, and coverage of the mass range. Teams on multiple continents are attacking this from different angles simultaneously. At the University of Washington, the Axion dark matter experiment has been running for years and is now in its most sensitive phase yet. Its cylindrical resonant cavity sits inside a superconducting magnet, producing fields 8 times stronger than those used to image the human body in a medical scanner. The cavity is cooled to temperatures near absolute zero. Quantum amplifiers at the edge of physical limits amplify any signal before it dissolves into thermal noise. When the experiment finishes scanning its current target range with no signal, it will immediately shift to the next section of the mass spectrum. In Europe, a different approach called the Any Light Particle Search uses a technique called light shining through wall. A powerful laser fires photons at an opaque wall. In the presence of a strong magnetic field, some of those photons might convert into axions before hitting the wall. Axions, interacting only through gravity and very weakly through the magnetic field, pass straight through the wall. On the other side, another strong magnetic field waits, hoping to convert those axions back into photons that a sensitive detector can catch. If a photon appears on the other side of a wall that no photon could penetrate, an axion made the trip. In Japan, South Korea, and the United States, new experiments target different mass ranges using different resonator geometries. Some use microwave cavities, others use nuclear magnetic resonance techniques. Some are exploring whether the Earth itself, moving through the dark matter halo of the Milky Way, creates a detectable axion wind that instruments on the surface might register. Underground laboratories are the preferred homes for many of these experiments. Gran Sasso in Italy, Kamioka in Japan, Sanford Underground Research Facility in South Dakota all sit under enough rock to block cosmic ray backgrounds that would otherwise overwhelm faint signals. The same shield that makes them ideal for neutrino experiments makes them ideal for any search where quiet is essential. A new class of detector called a quantum sensor is entering the field. These devices use individual atoms or superconducting circuits in quantum states to detect extraordinarily small energy deposits, far below what classical electronics can register. The sensitivity improvements they offer over the next 10 years could compress what would otherwise take decades of scanning into a much shorter timeline. The collaboration is international and genuinely competitive. Teams race to cover mass ranges before each other. A detection anywhere in the world would be immediately confirmed by other experiments already running. The redundancy is deliberate. A dark matter discovery needs to survive independent verification before the physics community accepts it. The search is real, active, and closing in. Whether it finds something or rules everything out, the answer is coming. Every time physics has faced a crisis, the resolution required throwing out something that felt obvious. Before Einstein, space was fixed and time was universal. Every clock ticked at the same rate everywhere. The idea that two observers moving at different speeds would measure different lengths and different time intervals sounded absurd. Time stretching, space compressing. Those ideas violated every intuition built from daily experience. Einstein threw out the intuitions and followed the math. Before quantum mechanics, physical objects had definite positions and definite velocities at all times. The idea that an electron has no specific location until you measure it, that it genuinely exists as a spread of probability until the moment of observation, violated the common sense picture of a physical world existing independently of measurement. Bohr, Heisenberg, and Schrödinger threw out that common sense and followed the experiments. Both revolutions required abandoning something that felt so obviously true that challenging it seemed like confusion rather than insight. The missing particle problem may require the same kind of sacrifice. The specific thing that might need to go is the assumption that space and time are continuous. Every physical theory ever written treats space and time as smooth, infinitely divisible backgrounds. You can always zoom in further. There is always a smaller scale. This assumption is so deeply built into the mathematics that it feels more like a fact than an assumption. But loop quantum gravity, one of the serious competitors to string theory in the quantum gravity space, proposes that space itself is made of discrete building blocks at the smallest possible scale. The Planck length, roughly 100 billion times smaller than a proton, would be the minimum possible distance. Space would be a network of interconnected nodes, not a smooth sheet. Time would advance in discrete ticks, not a continuous flow. In a discrete space-time, particles as we currently conceive them might not be the fundamental objects. The particles of the Standard Model might be patterns in the network, collective behaviors of the discrete structure that look like particles from the outside. The graviton, from this perspective, is a ripple in the network at scales we cannot probe. The Standard Model's missing particles might be missing because they are not actually particles. They are features of a deeper, discrete structure that our continuous space mathematics is approximating, accurately in most regimes, but wrongly at the boundaries. The practical implication is that the next revolution in physics might not come from building a bigger collider. It might come from developing entirely new mathematical frameworks, ones that do not start from continuous space-time, and seeing what they predict for observations we can already make. Gravitational waves are one such observation. The Laser Interferometer Gravitational Wave Observatory detected its first signal in 2015 and has since catalogued dozens of merging black holes and neutron stars. The gravitational waves carry information about extreme space-time dynamics. If space and time are discrete at some level, those ripples might carry subtle signatures, tiny deviations from the smooth predictions of general relativity that future detectors sensitive enough to measure them might catch. The search for missing particles might, in the end, force physics to ask whether particles are the right language at all. Step back from all of it and look at where things stand. The sterile neutrino, the particle that was supposed to be a fourth ghost neutrino, interacting with nothing but gravity, has been ruled out at the mass scale where anomalies pointed. Two separate experimental programs, one using liquid argon technology at Fermilab, one measuring electrons from radioactive decay in Germany, closed the most accessible hiding spots with definitive data. The anomalies that launched the search traced back to measurement errors in older detectors and nuclear physics calculations. The ghost particle, in its most testable form, is gone. The graviton, the particle that carries gravity and would unite quantum mechanics with general relativity, remains theoretically demanded and experimentally unreachable. The mathematics describing it are precise. Its properties are known from indirect evidence, including the speed and behavior of detected gravitational waves, but catching a single graviton requires a detector with the mass of a planet, and even that would only yield one signal per decade. Some physicists now argue gravity might not be quantum at all, that the graviton is a mathematical echo of a question physics is not yet equipped to answer correctly. The axion stands alone as the last serious candidate for dark matter that current experiments can reach. Born as a solution to a mathematical flaw in the strong force, it turned out to match the requirements for dark matter almost perfectly. Experiments worldwide are closing in on the theoretically favored mass range using supercooled cavities, quantum amplifiers, and magnetic fields far stronger than anything found in nature on Earth. The decisive phase of the axion search is happening right now. What gets built next is a mix of refinements and leaps. The high luminosity upgrade of the Large Hadron Collider will push particle collision energies to new records within this decade, searching for any heavy new particle above current thresholds. A proposed future circular collider in Europe, roughly 3 times the diameter of the current one, would reach energies 6 times higher, putting supersymmetric particles firmly within reach if they exist at any theoretically motivated mass scale. In space, the next generation of gravitational wave detectors, including a planned space-based interferometer called the Laser Interferometer Space Antenna, will measure gravitational waves at frequencies and sensitivities impossible on the ground, carrying information about the most extreme events in the universe. And the Axion experiments, scaling up in sensitivity every few years, will either find the particle or rule it out completely within a time frame shorter than most careers in science. The answer to any one of these searches changes the picture entirely. A confirmed axion rewrites cosmology, validates a 50-year-old theoretical prediction, and opens an entirely new experimental field. A confirmed supersymmetric particle restores the hope of a complete unified theory and points directly toward the graviton's theoretical home. A confirmed deviation from general relativity in gravitational wave data could signal the first experimental hint of quantum gravity, pointing toward the deeper framework everyone is looking for. And if all of them come up empty, physics faces its most honest reckoning in over a century. The rules would need to be rewritten at a level deeper than any previous revision. The assumptions baked into every theory since Newton about what particles are, what forces are, what space and time are, would be on the table. The universe has always been stranger than expected. Every time physics thought it was close to a complete picture, the picture turned out to be a doorway into a larger room. The missing particles are pointing at the next door. Whether the door opens into a particle, a new symmetry, a discrete space-time, or something no one has named yet, it is the most important door in science right now. And every experiment running tonight is trying to find the handle.